Yeah, hello everyone. Uh, Now this is time to start second talk. Here we have a great speaker, Professor Octavia Dobre, and topic of second talk is intertwining wireless advances with quantum computing, a leap beyond 6G. So let me introduce her briefly. Professor Octavia Dobre is a professor and Canada Research Chair Tier 1 at Memorial University, Canada. Her research focuses on next generation wireless networks, optical communications, and underwater communications. She has authored over 600 plus publications and received more than 10 Best Paper Awards, including IEEE ComSoc, um, uh, Henrich Award. Professor Dobre currently serves as a Vice President of Publications for IEEE ComSoc. She was the founding editor-in-chief of the IEEE Open Journal of the Communication Society, editor-in-chief of IEEE Communication Letters, and IEEE ComSoc Director of Journals, a former Fulbright scholar and IEEE distinguished lecturer. She is an elected member of Academia Europea and European Academy of Sciences and Arts, and a fellow of IEEE, EIC, CAE, and the Royal Society of Canada. She is also a clarivate, highly cited researcher. So let's welcome Professor Octavia for her talk.
Well, thank you so much. Oh, that one works. Thank you so much. Thank you so much for the introduction, and well, I'm really glad to be here and to give this talk. So we are thinking, well, bridging wireless communications and quantum computing. So I'm not going to talk about quantum communications because that's a little bit different, you know. It's more really about quantum computing and how we can support wireless communications with that. So why are we thinking about this topic? And well, you'll see also the evolution of quantum computing, because I think it's about time for us to start looking into the topic. Quantum computing has evolved significantly. I mean, think that around the globe, the investment by 2023 was like 30 plus billion US dollars, and by 2030 it will be over 120 billion dollars. I'm not really sure how it is in Taiwan, but in Canada, there is significant funding in quantum technologies in general, and not only in Canada, US, UK, and other countries. Okay, well, but before actually going into the topic, I'll tell a few words about us. So this is our campus, basically. We are situated in the most eastern point in North America, and this is the university. And this is actually the Marconi Tower, where the first transatlantic wireless transmission took place from UK to my city, St. John's. This is actually here, the university, because the pointer doesn't quite work, and our lab. And well, we also have a Canada Excellence Chair. I think he visited you, and we founded Quantum Communications and Computing Center. Okay, so this is my research group doing work in different areas. And you can see that we have actually terrestrial, non-terrestrial networks, but also including maritime and underwater, because we are right at the edge of the continent. And we try actually to build a prototype also with drone and iSAC, right, on the sensing. You can see here some...
PPT, the presentation is not working online.
Oh, okay. Online.
the PPT is being presented. Is the presentation visible?
Yes.
Can you just move some slides to kind of just
Sure,
cross
sure.
check? Yeah, thank you so much. Yeah, it's working.
Screen, because when you put it full screen.
Okay, 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 okay. I'll just ask.
This is not the screen.
This one, right? Is the presentation visible now?
Yes,
Yes.
yes.
Okay.
Okay, fantastic. So, okay, well, actually we have all the equipment and we want to build a prototype also with the underwater, above water, maritime and drones. And you can see here some software-defined radio modems for the underwater, preparing them, testing them in the tank. Well, although I'm talking about quantum, but the underwater channel, it's very challenging. It's double dispersive. We look at new waveforms, and you see OTFS here, because that's really good for Doppler and dispersion. Some other areas of research that we are doing, a little bit of pinching antennas, following in Professor Ding's step, the Y paths that he mentioned. But nothing really as extensive as he has been doing. And finally, because of the funding, and also because of the trend of the industry, we look at how quantum computing can support wireless communications. In fact, I'll talk a little bit later on. I have another slide because it's not only quantum computing, quantum communications, it's quantum sensing. Quantum radar is part of that. And we are also looking at some other technologies in quantum. So basically the question is, okay, we have a classical paradigm now when we talk about ISAC, when we talk about sensing, about communications, but maybe in some decades, I don't know, 2 decades. I'm not talking about 7G, way beyond, most probably how these technologies, quantum technologies, will work together and together with classical technologies. That's a very good question for the students for the future. Okay. Well, I'll have an introductory part on wireless networks, and many of you know those things, but I'm trying actually to make a point for quantum computing here. And, for each generation certain of wireless networks, ITU comes up with a vision, right? What are the KPIs, actually the use cases, the KPIs, and then we all start the invention phase, right? Running like pinching antennas. It's a new technology, right? OTFS, a new waveform. Are those actually, well, and proof of concept that Docomo did for pinching antennas, are those technologies, some of these technologies going to be standardized by 3GPP? Not necessarily. But then even if they are standardized, are they commercialized? Because in the commercialization stage, we have the service providers. It's about really, investment, capital investment. Well, for example, the integrated access and, well, what is that? IAR or AIB, right? Or something like that wasn't actually commercialized. Yes, yeah, IAB, right, exactly. So it wasn't really commercialized because
sorry.
Yes.
The presentation and the online, they are not synchronized, so we can see a different presentation in both the screens. Sorry for the interruption.
That's fine, not a problem. So can you see now? Maybe I'll run in. So what about now? Can you see me changing the slides?
Yeah, now I can see.
Okay, okay. I'll go in this mode. I think that also in the room we can see, right? So so basically, okay, in 6G now we certainly know that we expand the 5G pillars, and as Professor Jiguo mentioned, we have so many papers and so many ideas on integrated sensing and communications, which is another pillar. But actually, integrated sensing and communications, you will see in the next slide, it will be already part of release 19 of the standard, how are we doing that? Because it's great to come up with ideas. It's great to publish papers, and this is how we practice. And again, we come up with really amazing ideas. But at the end, if you think about the system, how we are going to do that. Well, because the system, you have the frame, right? You have the frame that 10 milliseconds. You have subframes. You have resource blocks. You have the same. Actually, 5G is built on 4G structure. You have OFDM. You have pilots. Pilots actually for different issues. And what type of pilots do you have? Okay, well, for some synchronization, something that I asked Professor Jigu about, for channel state information and so on. So you'll have now pilots for sensing, but also how can you place the pilots because of the spectral efficiency, but also because of the accuracy in sensing, right? What about radar, if you think about sensing, because you have a continuous waveform? Well, that's part of the standard as well, or it will be part of the standard because your accuracy will be, better. But what happens when you put a continuous waveform, in the structure of OFDM? Well, it can leak, right? It can create inter-carrier interference and all that. So this will come actually in the standard, but certainly it's much more, will be much more than that, and we look towards the future. Okay, so that's another pilot. Integrated AI and communications, it's another pilot, another pillar. So what is this about? We all know, again, tons of papers about AI, different type of AIs at different levels, right? Okay, well, where will be this one in the standard? Also release 19, actually. What it is about? Well, it is about channel state information. It is about beamforming. It is about, let's say, user association, about predicting user mobility, load balancing, energy saving. So we really will have AI, in the standard. But also, well, we had actually already in 5G AI in the core for different issues. Okay, now, and we have now, different technologies, different ways of transmitting information, for example, semantic communications. But where quantum computing comes into play, first and foremost, and most probably it will be included in a standard. Well, here, security, first and foremost. I mean, AI, yes, we can use it for security. It's a double-edged sword, right? We can identify the malicious traffic, the malicious nodes, isolate them, or, we can actually poison the data, the algorithm, the model. But then quantum computing, and I'm sure that you know about it, there is an algorithm called Shor algorithm, and I'll talk about it a bit later on. That gives us exponential speed up when compared with classical algorithms, and this algorithm is used for factoring integers. So basically it challenges the status quo of security, right? Also quantum computing, actually a bit quantum communications, I would say, it helps security with quantum key distribution. And I will talk a little bit about that in the next slides. What about quantum computing for integrating sensing and communications? Well, I mentioned the standard makes it very simple, right? Because, and again, it needs to operate. So it needs to be related to the structure of the frame, everything that we inherited and we have also in 5G. But what about if we want to know the 3D scenery in the future? What about running, this AI, but very complex AI, which may need a lot of training? Well, people say, well, okay, well, training is offline. Well, what about in dynamic scenarios, How quantum computing can help us in, to resolve these issues? First of all, Quantum computing, and I'll talk a little bit about fundamentals. It uses a parallelism and superposition. So everything can be done absolutely much faster. It can handle high dimensional features and very large size, data. That's one thing. Another one, and I will show you an example in the next slides, like in a neural network, you have so many parameters that you optimize. Pulling quantum machine learning, you can use only a few parameters. So, okay. Hopefully, I'm trying to make a case here, and we'll see what the future holds. Well, in terms of the standards, because I mentioned the standard, the first standard for 5G was released in 2019. And see, this is what I was wondering about: scalable OFDM-based air interface. So basically, 5G inherited that, only that it makes it scalable for short transmission time, right? Different sub-carrier spacing and different, symbol duration, useful symbol duration. So how would that match with all the technologies that we are developing? Because at the end of the day, if we want to deploy those, there is a cost of deployment, right? But we are academia, so we can reach the sky and have invention, that invention stage that I mentioned about. So it's okay, right? But sometimes we also need to think about practicability, especially if you go and work for, Ericsson and other companies. Okay, well, a little bit about, the standards, because also I want to make a case here. Yes, yeah, so it was IAB, right, okay, thank you. So, right, so IAB, Integrated Access and Backhaul, made it to the standard, but not implemented, right? Not commercialized. That's release 16. I mean, all the time we have improvement in the standards. For example, here, MIMO is really about channel state information, about mobility of the users, and for example, dual connectivity with two antennas connected to a user. And then also we extended the FR2, right, the frequency band. We introduced non-terrestrial networks, hubs, and satellites. Okay. And I'm not sure if the audience will see when I change the slides. Okay. But also is not only about the network, and those technologies.
And the PPT we made full screen.
Okay.
Sorry.
Yeah. Okay. I don't know. So that's I'm not going to resolve that problem. So I don't know. Yeah. Okay. Extended. But we also have new devices, right? Like extended reality, and we know devices, and we know what it requires. But also, for example, red cap devices, right? Which is our native 5G, reduced capabilities, less number of antennas, less, let's say, MIMO, reduce MIMO, reduce RF chains, reduce power consumption. They are used actually for Internet of Things. And all the time, more and more improvements. So now, release 18 starts 5G Advanced, and you can see here what I mentioned about AI and machine learning, right? And certainly it will be used for indoor positioning. More enhancements in everything else. I mean, I'm not going to go through all these details. I can do that, but offline, because actually that's not the point here. As I mentioned to you, release 19, which is not out yet, it includes ISAC, right? So pilot and continuous waveform, it's already there. And certainly we look at alpha FR3, although it's not allocated yet, it will be allocated, and a conference WRC, right? In some years. All the time we are ahead of that. But other devices, ambient IoT, and again, more improvement. If I look at dual connectivity, I have a user connected with two base stations, one working in FR1, one working in FR2. So, what I'm trying to say here, I mean, maybe 2 points. Again, the sky is your limit. You can go, with the innovation wherever you are, but then it comes the implementation, right? But also the second point is that the network has become more and more complex, that everybody knows, but hopefully I made the point. And here we look at the hyper-connected world, and we talk about terrestrial and non-terrestrial and all the technologies, but I would actually say in the non-terrestrial also maritime comms and even underwater, because this is really, ocean is 70% of this globe. So all these type of communications have been intensified, recently. I was in a panel, and certainly computing, makes it's part of the network. So I was in a panel, and people were saying AI and more AI and more AI, different type of AI, right? Agentic AI and all that. But here I am, and I say, what about quantum AI and quantum AI and quantum AI in some future, Again, what exactly can you do in terms of processing? Well, I can tell you that NTT, Docomo actually in Japan use quantum computers, D-wave quantum computers, I'll talk about those, to predict mobility in the network. And this experiment was done, this trial was done actually last year. And an algorithm that they ran with their classical computers, I don't know exactly the specs, but it ran in 27 hours for training. Actually, with the D-wave quantum computers, it ran in 40 minutes. So maybe that will help Professor Jigwa's work on positioning and on the 3D scenery, and maybe dynamic, channels and dynamic scenarios, because then you can predict much faster and also with high accuracy. Okay. So as I mentioned, what about, some people talk about quantum communications. I'm talking a bit about quantum computing. Actually, one student of mine is looking at ISAC when we do quantum sensing and classical communication. And there is an algorithm called quantum illumination that we use in quantum radar. And actually the performance is very good in low SNR, very low SNR, very scattering environment, and not with too high power. And that power, you can use it actually for communications. So we are almost done with that work. We'll post it on archive soon. So I'm calling that quantum paradigm with all those technologies. So it's very interesting to see what the future is going to bring. Okay. A little bit of quantum computing evolution. Before giving you some examples, because, I'm talking with to an audience who has significant information on communications, right? But maybe less on quantum computing. And I organized this information about evolution on 1G, 2G, 3G, 4G, 5G, right? And again, I'm learning myself actually at this stage. So in the 1G era, well, the actually concept of using quantum mechanics to quantum computing came up. And then in the 84, the first algorithm, quantum key distribution, was developed. It's called BB84. Actually, one of the people who invented it was a Canadian, is a Canadian. And let me tell you how simple the idea is. So you have Alice and you have Bob, and this is based on photons, okay? The photons are qubits. I'll talk about qubits next. But anyhow, just imagine, right? You send photons. And then you have some bases for Alice and Bob. And let's say polarization, right? The two polarization. And you send, and then Bob, after this transmission, actually you do measurement and you get back the classical information. And then they don't change the bits, the final result in the classical information, but they exchange the bases. And wherever they have the same basis, they keep those bits, right? And they form the key. But now imagine that an Eve comes and wants to intercept information. Eve will need to have a basis and get that number, but then we'll need kind of to retransmit somehow. So it changes something, right? So if the number of errors, well, okay, then Alice and Bob, after getting all those bits, they exchange a certain number of bits, and if the error exceeds a certain threshold, they say it was an Eve. But that's really ideal, right? But anyhow, it was the starting point. Okay, so other algorithms for quantum key distribution, Eckhart in 1991 called E91, that's based on entanglement, right? That's a new term, and I'll show you what entanglement is. So there is such a strong correlation between qubits that you do not see in the classical information. And actually this entanglement is the basis of teleportation used also in quantum communication. So there are very, very new concepts. Not very difficult, but very new concepts, okay? And then more algorithms. The Shor algorithm that I mentioned, integer factoring, Grover algorithm, which is to search an element in an unstructured database. It gives you the lowest bound in terms of queries. And this algorithm actually represents the basis of other algorithms. You use it for signal detection. Lioche-Hans also has quite support on that. And then, you know, the hardware development began. And then the point is, okay, we want more, like we want more and more bits, we want more and more qubits, you know, and you'll see what a qubit is. And then it was the term of quantum supremacy, because Google actually showed that a problem which was solved in some 10,000 years was solved, you know, in some, you know, hundreds of seconds. Where are we now? I mean, if you check the IBM website, IBM is a big player in that, and many others. I'll show you in the next slide. You know, they want, again, more and more qubits, this scalability, right? To scale up. But the problem is that not all these qubits are so-called logical qubits, you know, with error correcting, you know, logical qubits. Because let's think about a neural network. We know where the, let's say, errors can come in training and all that. But think that your computing platform will introduce more errors because it's not fault tolerant. That's another error. So this is why we are here at the error correcting phase. And also all these companies want to see those investments, you know, of billions of dollars, where does it go? I mean, it has application in finance, in drug discovery, but in what other areas, right? So we look at applications. Actually, we have access to the Huron IBM computer in Canada, 153 qubits, and we run, you know, different algorithms on those computers. I mean, I would say this one, how to call it? Maybe I'll call it quantum wireless 00, right? Generation 00, 0G, or I don't know, -1G, something like that. So, and even in terms of computing, right? I mean, long time ago, you are very young. I mean, you run software now on different platforms. You don't care. It's like, oh, right, okay, it has an NVIDIA, whatever, you know, or whatever. But you don't really care what's inside it, you know. But at this stage, we kind of know a little bit what's inside, you know, that computer. So we need to know the hardware. We need to know the software. We can also develop new software algorithms that we did. So a little bit about hardware. IBM, Google, Intel, they use superconducting. Those run at millikelvin cryogenic temperatures. Yes.
For your research,
yes.
quantum simulators like circuits,
right? Yes, I use simulators, Qiskit and Penny Lane. So Qiskit is actually the software platform of provided by IBM. And Penny Lane is the software platform provided by Xanadu. Both actually Xanadu is a Canadian company with headquarters in Toronto. IBM, we also have an IBM quantum computer, and we are very in strong connection with IBM headquarters in New York City. I mean, if you start using Penny Lane, it's easy to go to Qiskit. Penny Lane, I mean, this company, Xanadu, were in a way pioneers in quantum machine learning. But also now IBM has quite a few tools for machine learning. They work actually with different libraries. I think Qiskit might work with Scikit for and Penny Lane works with TensorFlow and I think another one. I might be wrong. Yes, we do, but we also have access to the computer itself. Okay, yeah. I mean, if you simulate and use the simulator on classical computers, it will run very slow. You need to have, high performance computing stations in order to be able to run those. And it really depends on how many qubits you have. I mean, if you have 3, 4, 5 qubits is okay. But if you go to 20 qubits, yeah, something like that. Okay, so superconducting, actually, yeah, it goes to very low temperatures, cryogenic temperatures, millikelvin, because first of all, the noise, the thermal noise, will actually affect the quantum state, So, and we work with gate circuits, and what are some parameters? Because there are many parameters, to look at. How fast the gate is, right? And also what is the coherence time of a quantum state? Because if you have a very deep circuit and that doesn't remain in that state, you cannot really process it. Because, yeah. Okay. There are other technologies and, with different actually, let's say, coherence time, different speed. I can tell you some order of magnitude. So it's trap ions, neutral atoms, and think that all these particles, I mean, in these particles, a quantum state will be actually encoded. And when you have a gate, you can have different quantum states, and sometimes you need to do correlation between those. So you'll see some circuits, not only words, in the next slides. Photonic, but it's also difficult to entangle the photons. Well, actually, Microsoft this year came up with a new technology. It's not in quantum state is not encoded in a particle. It's encoded, well, I don't know, in some modes of operation to a superconductor. But the good thing is that that's fault tolerant. And you heard me talking about D-wave. This one uses quantum annealing. And the annealing from optimization, right? And actually the term annealing comes from the thermal, material science. You heat a material, then you slow down, you cool it slowly, and it reaches a minimum state of energy. It's the same principle here, but using quantum mechanics. Anyhow, and this is a computer used for optimization. Those optimizations, right, that we just talked about. So it's really for optimization. It's not a general purpose computer. Okay, so let's look at some algorithms. Exponential speed up. I mentioned to you short algorithms for factoring integers, but there are some algorithms with quadratic speed up, like Grover algorithm that want to search through an unstructured database, and some optimization algorithm. Actually, this is for quantum approximate optimization algorithm. And this is something approximate. This is called variational quantum eigensolver. Anyhow, I mean, this variational, what does it mean? Okay, at this stage, the stage of quantum computing is NSYSU, noisy, intermediate scale. Quantum, because we said we want fault tolerance, right? We want to scale up, but now it's intermediate scale noisy. So at this stage, the solution is to use hybrid between quantum processors and classical processors. And you use actually variational circuits, variational algorithms. Let's think that you have a problem to a function, want to minimize, okay, the function. This is encoded in a quantum state, which is parameterized, and you find the parameters using the classical algorithm. It's a bit, I asked IBM because I don't really know, I haven't seen that. And it's like, oh, it's easy to be done. How? If you ask me, I'm not really sure, right? Also, quantum machine learning, and here I show only neural network and support vector regressors, but you can see the literature, quantum reinforcement learning, quantum large language model. So it's coming, right? Slowly. Again, because of the NSYSU era, like if you have a deep neural network, you may not implement it in current quantum computers, but partially, part of the neural network, and I'll show a toy example, you can do it, and it speeds up the computation, but also requires less parameters, it handles lots of data. Okay. A bit of basics, and maybe if you relate the basic with what I talked about, then maybe it makes a bit of more sense. First, we prepare the state, quantum state. Then we use some circuits. Okay, there are also quantum technologies that do not use circuits, but we with IBM, with Xanadu, we use circuits. Okay? So we do some circuits operation, and then we do measurement. We collapse the quantum state onto the classical information. This is another circuit, basically, that we are using, and I'll show you next. Okay. So representation of quantum information, because I talk about that. So if you have classical B01, that's it, right? But now a quantum state actually for one qubit, right, 0 or 1, can be represented to this block sphere, block being Felix block, so scientist. And you have state 0 and state 1. These are the CATS notations. And actually everything from, quantum mechanics translates into the linear algebra. So we work, with what we know very well. Right? So vectors, and then this is a quantum state with the superposition of states 0 and 1, and with some probabilities which can be complex valued numbers. And actually, this gives you the probability to be in state 0 or to be in state 1, right? Or you can actually represent it in terms of angles. So that's a quantum state. And then gates. These are again very, very simple, very well-known circuits. Poly X, poly Y, poly Z gate. So it has only one input, only one quantum state and one output. Every circuit is actually characterized by a unity matrix. And this is why you see here this matrix. So what does this matrix do? Or this circuit, instead of being 1, 0, 0, 1, maintaining the 0 state and 1 state, it actually changes the state, right? All is that it introduces a phase here in the 1 state. Hadamard, it creates superposition between the states. Control C naught, and we just say C naught gate. So basically, in this case, you have 2 states, quantum states, and then the one on the top controls the one on the bottom. So if this is 0, 1, and this is 1, then you'll have 1, 1 at the output. So 0, 1 is here, but the column corresponds to the 1, 1. So what creates, it creates a correlation in a way between these 2 states. And again, I'll show you an example. Yes. Yes, please do. Is it okay? Yeah. Okay, thank you so much. Thank you so much. So here, you know, you have a circuit, as I said, that's the circuit and then the measurement. So let's see, you know, that's the quantum state and the quantum state. How we represent the operation, actually, it's the tensor product. So this is characterized by a matrix. This is the Hadamard, and this is the identity, right? First, we have this one, identity and Hadamard, and you can do that. And then we have the C node, you know, multiplied by that result. And it gives us a matrix. So all these circuits, you know, it's characterized through this matrix. Or we can think in a different way. We have state 0 at the input, and actually all these systems tend to stay in a low energy state initially. You know, this is the state 0 state that we start with. And then you think here, okay, well, actually here we have another quantum state, you know, which is again, you know, well, the product in a way, but between the 0, 0 state, right? And then, you know, actually, if you work in this area, you know that Hadamard, you know, what you have here, basically your Hadamard will change the state to a plus state. And you can do that with the matrices. You can calculate, you know, and do that with the matrices. What is the plus state? Is 0 state plus 1 state divided by 1 over square root of 2, which is corresponds to the Hadamard matrix. Right? What about here? I have the C naught, you know, gate. So whenever this one is 1, it will change actually my bottom qubit into 1. So I have 1, 1. And this is actually a very well-known state called Bell. It's one of the 4 Bell states, because now you have 2 states, right? You will have actually 4. You'll have 2 qubits. So why it is so famous, Bell state? Yes, because it shows entanglement. And I didn't talk here about the measurement. And, you know, what about measurement? We said, well, we actually projected on some basis functions. So, okay, let's look at that. We said that this is a probability, and this is almost related to a probability, right? So what would be the probability to be in state 0, 0, 1 over 2? What about state 1, 1, 1? The probability is also 1 over 2. So if I use these standard basis functions, I got this result with equal probability. So then in the classical computation, you'd think, well, what the heck, you know, what that, how is helpful to me, right? Okay, well, it's very helpful because think about quantum key distribution that I mentioned about. If we share something which is entangled and there is a need trying, you know, to get that information, it will not, because we can detect it, okay? Because the correlation is much stronger than in the classical systems. Anyhow, there are some inequalities, So because that's very important. Because when you have entanglement and you share again entangled, you know, qubits, then you can do teleportation. You can transmit to Alice and Bob. And that's really the basis of quantum communications. Alice and Bob, they share, you know, such an entangled qubit. Then somehow, through some processing, through some gates at the end, they transmit classical bits, but they can get, Bob can get quantum state of Alice. But once they do that entanglement state is gone, you know? So it's really, we need more hardware, you know, to do a good job. Even if we actually do measurement in other bases, we get other states with equal probability, you know, and this is really the change, the significant change or difference when compared with classical communications. Let me give you some examples now. This is a very simple example. Okay, we have NSYSU, right, transceiver, and we want to do self-interference to cancel the self-interference here. It is Okay, full duplex, but in band full duplex, right? So we're transmitting the receive and transmit in the same time at the same frequency. And certainly my signal of interest will overwhelm the self-interference will overwhelm the signal of interest. I'm not going to talk about self-interference cancellation because that's another topic truly, right? You need to do actually self-interference even here, even in the analog, because you don't want to run those, in saturation. But anyhow, I'm talking in the digital domain, it will remain a residue. And although we know the sequence that we transmit is not as simple to do all this full duplex, self-interference cancellation. But let's say you have here a residual. Even for the residual, actually we split it into obtaining the linear component and non-linear component. And non-linear component comes from the fact of going through all these chains of non-linearities. We have done actually quite a bit of work. You can follow our work in collaboration with an industrial sponsor. What I'm going to look here again is the non-linear component only. And for the non-linear component, we consider a two example. We consider hybrid hybrid neural network, convolutional and LSTM. And we know what convolutional does, what LSTM does. But here for the LSTM, in terms of the gates that control the flow through the cell, then in terms of that, we use a variational circuit, a quantum LSTM. Okay. So basically that is replaced with some quantum circuits, variational circuits. What did I mention? Less parameters. So you have here 1, 2, 3, 4 parameters, but I'll start with the beginning, okay? Here you have classical information. What can be the dimension of this feature? 64, 128, right? Nobody's think that you have a neural network. Well, nobody is going to use here 64 qubits or 128 qubits, right? The idea is that with qubits, we can encode with a very, very few parameters. In this example, we just give, 4 qubits as input. But see, also in one of the slides, and let me go back because otherwise, what I said here, we need to prepare the state, right? So let's see how we prepare the state and then the circuits. Yeah, okay. So how do we prepare the state? See, we have here angular embedding. So basically, okay, so, yeah, need to go back. So 128, 64 dimension. Now, if I have 4 qubits, I need a very tiny neural network, to change the dimension. I do an embedding for each qubit, to bring it on this block sphere. And then angular embedding is one of them. So I need also to have dimension here between minus pi, right? Angular embedding, it means if I have here a number, I have cosine that number over 2 multiplied by 0 state plus sinus, again, multiplied by 1 state. So I place it somewhere here, okay? So each of those will be placed on the block sphere. Now I have some rotation, some circuits that rotate. They rotate each qubit along the x-axis. Why do you think that I'm doing that? Because in a neural network, I search, right? I search or I try to optimize to get the parameters. Now I'm doing rotations, and because I'm transforming all this, classical information onto this Hilbert space, right? So I'm searching in that Hilbert space. So I'm searching independently, right, for each qubit. But in a neural network, you have the weight, right? It creates, right. So what do we need? We need the correlation between them, connection. So we do that with the CNOT gate that I show you about. And then we do measurements. Actually, we project on the z-axis to have 0 or 1. But as I show you, that's probabilistic, right? So we need to run that a few times and to get an average, because otherwise it doesn't really work. Okay, but we have 4 parameters. rotations on each of the axes. Well, and this is the circuit actually for the rotation. And again, each quantum circuit is described to an unity matrix. Yes.
How do we determine which gate to use? What is the use case for each? How do we exactly design the quantum circuit?
We designed the quantum circuit. Qiskit also can help because now, they actually advanced that. But how to, for example, angular embedding, right? There are different types of embedding. This is only the phase. And this is a very simple circuit with a simple function, right? I have just a seesaw chain, and this is the two example. But there are other, more involving encoding, circuits, for example. So you can try and you can see which one, it's better for your application. And also after a while, you kind of get a sense of what to use. But also you think about the circuit, you think, okay, well, if I have those independent, then how do I make the connection between them, right? So anyhow, I'll also show other circuits, and maybe that will help. Right? Some results about the self-interference cancellation. You see that 4 qubits is enough. Otherwise, it doesn't make sense to use more than 4 qubits. And well, the algorithm converts much faster. Those are simulation results. It's not constant. The number of qubits is not very high. We are running other algorithms on the computer. And the result is much better with the classical one. Okay, well, this is really related to us as common people. Why you want to do self-interference cancellation? Because you want to bring that to the noise level. Right at the end, you want the SIL not to be very low. So we'll look at power representation. Okay, so another example for support to vector machine for the regress selection. Okay, let me see. And about the timing, you need to tell me when to stop, because I can talk a lot and yeah. So what I said, here we can have a very large, high dimensional features, right? And we encode that into n-dimensional Hilbert space, not necessarily this one. This can be a little bit misleading, but I don't know what other graphical representation to show you. And then we compute the kernel, which is the inner product. This is very, very fast, actually, because also this space gives you, again, all the high dimensional, you encode it in a, relatively smaller space. Think that if you have n qubits, then you have 2 to the power of n. 153 qubits give you 2 to the power of 153. Okay? When you say qubit and processors, it's not necessarily a power of 2. They have different numbers, 133, 1, because they also do whatever connection they can make in that physical, in that computer, that's the number. That's not a power of 2. And computing the kernel actually is extremely fast when compared with computing the kernel with classical algorithm. If you have, again, high dimensional features, actually it's kind of n log n rather than n to the power of 2 or n to the power of 3. And after that, you actually collapse that into, the classical information, and you can run your SVM with this kernel. Okay? So this is again an example of hybrid. Now I said here encoding, right? How do we encode? Those are circuits. Again, those circuits. Some examples of circuits. Look, you have different inputs, Hadamard, create superposition. What is this one? Rotation around that axis, right? For each of them in that block sphere to search the space. And then I have here, okay, see, another circuit rotation around x-axis, a rotation around y-axis. And it's much deeper. The circuits are much deeper. And I should tell you, and if you do the multiplication of matrices or whatever, the result here is the same as the result here, and it's the same as the result here. So then the question is, why do I need all these deeper circuits, right? Because we talk about time and coherent time and fast time, because we search a space. And when we rotate only around the z-axis, we search a space not so much. But actually this gives me, if I stop here, it gives me rotation and amplitude changes because it changes in that sphere, in a different way. It searches the space, more profoundly. And I think that maybe you asked me about why we do not have, how we know the circuit or the correlation, or, this is the same, circuit as in this case. But what we add here, C naught and another rotation. So we kind of create entanglement between those independent qubits. But this would be, think about that. We search, but also we entangle them. So this is really the case for complicated, cases that you may have. And let us look at some results. Poly X, poly Z, poly Y, well, they shouldn't give us the same result. I can tell you why they didn't give us the same result. But the one with entanglement and all that, we don't need that in this complex, in this simple case, right? This is way more complex. And actually, we SDR, we do better, so. Okay, how much time do I have? 10 minutes, okay. Let me see what I'm going to. Say in 10 minutes. Okay, there are different concepts, okay, in quantum computing, and it's a tool at the end that we can use for communications, right? We need to be actually familiar with these algorithms. I think quantum machine learning would be much easier than working with quantum optimization algorithms. I forgot to mention to you that in case of quantum optimization algorithms, actually those are really applicable to combinatorial problems, mostly. For example, we do user association or, like spectrum allocation, we do, routing, so these are really good. For quantum optimization, you really need to reformulate your problem such that it fits kind of the structure of those algorithms. And that's its QUBO or icing, way of writing it. Quantum machine learning is much more flexible, I would say. And another algorithm that I mentioned about was Grover. Grover, again, is to search through a database which is unstructured, right? And if we think about maximum likelihood and its complexity, right? Maybe you search for that symbol, right? Using those type of algorithms. This is what we've done. Okay? You cannot do that with Grover, really, because Grover, you need to know the element value that you search, which you'll know, and the multiplicity order. Okay. I'm just trying to convey, something relatively complex in a very simple word. So, why Grover works so fast? It is like spinning a wheel. But I know here how fast to spin it. If I have, more solutions, multiplicity, I spin it at lower speed. If not, I spin it faster. There is also a probability of failure of that algorithm, which can be calculated actually analytically. And there is, again, this algorithm gives you the lowest number of queries of that database. But on top of that, there are other algorithms like known element unknown and both unknown And we use this Dürr and Hoyer algorithm actually. And well, okay, it shows you here how fast you spin, but you cannot spin it all the time. And you spin it slower first, and then you spin it faster. But if you spin it too faster, you might lose the solution, right? You kind of, yeah, you increase the speed and increase the speed, right? Something like that. But it's like the number of iterations. I mean, if you reach that database a lot of time and you spin it, then it needs to be, a limit. It needs to be a cap to do that. And that comes from Grover as well. And similar actually to with Dürr Hoyer. This is the complexity in the number of queries. N is the size of the database. S is the number of solutions in the database. So when the database, increases, well, certainly that the number of queries increases, but not as much as for the classical brutal force. Now we look at very, very simple, techniques, right? And yeah. And we consider the channel perfectly known. And you can see here in terms of queries, actually, the number of queries this is really good, actually, when compared with the classical, when the database is large, right? But what's the problem? I told you with Grover, even Grover has a probability of failure that we discovered. And actually with the database, okay, Grover, yeah, the probability of failure decreases, but these algorithms that are based on Grover that we use, actually first might be okay, but after that the probability increases because I use Grover and Grover again and Grover again, and I might miss the solution, so my probability increases. So when I look at the failure probability, well, it's not so great here because, if I apply that, if my space starts increasing, that my probability of failure of Grover or that algorithm based on Grover increases. So what happens here? We see this floor, right, for the bit error rate. Well, different spaces, right? Modulation order 16 and the number of antennas 4. And we see that there is a plateau, right? And you think, oh gosh, quantum would do better. Why do I get that at high signal to noise ratio? Because this is when our communication works well, but Grover doesn't really work so well because also the space increases and I have that error probability in the Grover itself. So the point that I want to make, instead of showing now maybe how great quantum computing is everywhere and at any time, my message is we need to research because not everything is great, right? And we need to see where exactly we can apply it. Yeah, that's my message here. And I almost conclude the talk. I mean, in terms of that example of self-interference cancellation, it was just a piece of toy, right? But what about we look now at, Professor Jiguo said, and maybe release 19, right? Like thousands of, antennas, or what are we doing, right? I talk a little bit about detection, but what about, it was very simple examples. So, but we really need to look at more complex examples, larger, size and different algorithms. We can come up with different algorithms, and we did come up with different algorithms. Quantum radar for ISAC, and certainly, quantum communications, but also in terms of scheduling, of resource allocation, of channel estimation, how well can quantum do, and how classical quantum can do. Some conclusions. I mean, we know that we have high performance computing, units or platforms at this time. When exactly those, or whatever we are doing, is going to exceed the requirements, are going to exceed what the current HPCs are providing. when exactly we need quantum. I gave you the example of Docomo, dynamic environment to predict the mobility, right, in 40 seconds. So the network becomes more and more complex. And again, does quantum computing really is able to resolve some of the issues? Where we can use it, really, machine learning, I can see, a big possibility, because again, we say in 6G even, and the future of the networks, AI and AI, agent AI, agentic AI, and so on. So I see a possibility here. Optimization, well, I'm also a beginner in this area, so but I do see the future of machine learning. But now really we are in the near term, we are in the NSYSU era, so we need to look at hybrid approaches. But at the end, maybe in some decade or more, I don't know, quantum compute or quantum technologies actually can become an enabler for secure communications, right, at a distance, to provide intelligence, to provide, sensing, and to provide at the end sustainable wireless networks. So yeah, I mean, we have a few projects where we use actually quantum, yeah, we work with IBM, with Xanadu, some universities abroad and in Canada, and this is a visit at the IBM headquarters last year in New York City. And this was the quantum computer, actually the 2 qubits. We took a photo with it, and on my slides in the center, you saw something similar. Well, that comes from the quantum computer, from the, superconducting quantum computer. And, some publications that we have along with my colleague, Trung Duong, and also, your professor. Yeah, so Kaushik and and other people also from Korea. We collaborate with different people in this area. So thank you so much. I understand that quantum computing is not really for everybody, but hopefully, some of the people will start working on that. Thank you so much. I can take questions.
Actually, the graph you showed us that when we are using purely quantum optimization methods, so there is a threshold we are reaching. After that, classical optimization works better than quantum optimization. But you also said that we are in the NSYSU era. So basically, the qubits are very noisy in nature. So maybe in the upcoming 2 or 3 decades, when we have almost noiseless qubits. So maybe that way purely quantum optimization might be better than classical optimization.
Yeah, so maybe for the audience, who is online, just to repeat, that I showed that maybe quantum optimization doesn't do better than classical. In fact, what I showed there wasn't really an optimization problem. Was more like a search through a database. It's like we search, we apply those algorithms, the Grover algorithms, and the algorithms based on Grover for that. So, but in terms of optimization, yes, I mean, I'm just saying that for now, you really need to formulate the problem in a certain way to be compatible with the quantum, computers. And typically it works for discrete variables, but think about, continuous variables, because those you can discretize them, but how much your precision is going to be, or you can have them as parameters in those variational circuits. Actually, your parameter can be a continuous random variable at that angle is, so you can design your circuit that way. But I don't know, I haven't seen a lot of work on that. Maybe I need to look into it. But machine learning, I think quantum machine learning, the development speed, it's much higher. And yes, we are in the NSYSU era currently. And I know that IBM has done quite some progress in error correction for qubit. And as I mentioned to you, Microsoft came up this year with another technology which seems to be fault tolerant, but there are other problems to solve them, like their scalability and the gate precision and other things, right? That so, but once these technologies evolve, are more mature, absolutely, I think that even optimization, will do much better, I would say. I mean, D-Wave also proved that, right? Because D-Wave is really for optimization. Yeah, I think that it's up to us now to come up with new algorithms and algorithms that fit us in our area better, because the algorithms are really tailored for different areas. For example, in exponential speed up, there are some algorithms, quantum simulation or something like that. Those are really, really good for drug discovery, because you have different, structures, different, and so many that actually it's much faster to process it than to simulate it with a quantum computer. But again, for our areas, what exactly are we going to do, right? Security will be part of standard, certainly, but it's really about the computing platform and, programming based, for those quantum computers. Yeah, I hope it's a long answer.
Yeah, thank you. I
Yes,
mean, maybe
sure.
I can ask something very
Sure,
quick. So I think it does look like that, quantum is quite useful, at least maybe, if not exactly 6G, but at least it was 6G advanced, 7G and beyond,
For 7G.
Yeah. So, I mean, we try to use some quantum machine learning in sort of like synergized sort of systems. So when you have iSAC combined with
Mhm.
non-terrestrial networks,
Right.
combined with meta surfaces, and we already
Right.
did like some
Right.
application
Right.
together. So I was trying to understand, okay, you do get some advancement in terms of the accuracy that you achieve with quantum machine learning, right?
Yes.
With kind of performance gets pretty high.
Yes.
But how about complexity? So are we adding on some layers of complex
Yeah.
system for quantum security, let's say? For iSAC, it's a big issue at the moment for,
Yeah, yeah. I mean, I wouldn't really say complexity, because in a way, how to say, see, when you simulate
Mm.
and simulate with a classical computer, maybe you look at, the timing, but that's not a
Or let's say
running time.
power,
It's
processing
not-
power, something.
It's not fair,
Mm.
because actually, the classical computer is not made to handle the quantum part. But when you do it on a quantum computer, it's significantly faster, right? So now, how much the space can be, the large space, or how much data you can process, how much your circuit can be, depth of the circuit. You really need to look at those
So
things,
does it
because there are
consume- yeah.
limitations, right?
Mm.
But in terms of processing faster, I mean, think that IBM, the gates, it's like nanoseconds, right? Something. So it's really, really, it can be very fast. It also depends on your design, But the coherence time, if I'm not mistaken, please don't take me for that. Maybe it's some microsecond, tens of microseconds, something like that. So you really need to design your circuit with those things, those parameters in mind, to see at this stage what you can achieve. But again, you look more at a hybrid solution, not only quantum.
So we
at
can
this stage.
reduce, the processing power in a way with
Yes,
using these
yes,
quantum computers
yes,
and so on.
Yeah, yeah.
And
I'm sorry, because
Yeah.
I'm not sure if I show you, I mean, you have, instead of having a dimension of 64 or 128 and dealing with that, you have just 4 qubits, and you rotate those, which is very fast. You have a CNOT gate, very fast. Everything is very fast in that variational circuit.
Mm-hmm.
And
so I think that makes it clear. So how about quantum communication as well? So let's say we were talking about some SIC usage and so on. We require some filtering of the signal receiver and so on. So recently, we have been coming out with that we don't really need this SIC unit. We kind of use some index modulation or something at the transmitter, and perhaps we can get rid of the decoding that we do generally with some multiple access. Do you think that quantum is like is sort of a catalyst to enable that, or you were saying that you reduced the SIC requirement.
Right. Yeah, I
Yeah.
mean, I think honestly, we kind of stopped working on this topic. We
Yeah.
just right now, as an example, because of the funding from the industry partner. But I understand that the industry partner consider our algorithms that we designed not quantum, classical, and went further and actually already have a prototype for MIMO. I don't know how much, MIMO, I mean, all the dimension, I don't know. But I think that doing quantum, I mean, if your channel changes, because your channel at the end, the SIC channel, the SI, will be affected by the environment. It really depends where your base station is, or and then if you can have actually very fast computing, it can help. And also all the correlations between the antennas, all that, it can help. But also, where do you put the quantum chip? You put it in the base station, you put it in the cloud.
Yeah.
Is it delay there? Is it so? Yeah, it's difficult to give you a clear answer.
Yeah.
Yes or no?
No, it's going on, but let's.
It's going on. It's going on. It's going on. Yes.
Thank you for the wonderful talk. And so it gives quite a nice perspective for my talk tomorrow, which is on quantum as well. As a researcher, so right now the quantum computing that you're using is mainly on IBM's Qiskit. And so for many researchers, it's quite expensive as well. It's just 10 minutes free for a month. But anyway, since those cannot do anything, but since those quantum circuits, we are currently using only 2 qubits or 4 qubits. So it happens in seconds. So that's not an issue. But I would like to know a bit about the other Canadian company that you mentioned. So, yeah.
Do you mind if we actually show the presentation? Or if not, it's okay. Yeah, if not, it's okay. So, yeah. Okay. It's not very good, right?
Not.
Okay. Yeah, well, IBM has invested significantly, massively, right, in this technology. Also needs to get something out of that investment, right? It's providing quantum computing platform computers across the world, right?
Yeah.
Actually, I think that Korea purchased one recently, a quantum computer from IBM. I'm not sure if Japan, but yeah. Indeed, IBM, I mean, if you can connect to a quantum computer, it makes a big difference. As for my team, for 10 licenses per year, the price is $50,000 Canadian dollars. For the entire university, because now we got sponsorship from ExxonMobil. ExxonMobil, it's actually a company for oil and gas, American companies, maybe you know me or maybe you don't. But they, I mean, just imagine how much traffic they have with their vessels across the globe, distributing this oil, and what are the requirements of different countries and all the optimization problem of the routes and all that. And they have actually, ExxonMobil has a division in quantum computing for their applications, right? And they are huge players, huge money. So they are sponsoring our access to quantum computers across the university for courses as well. And yeah, and that's about 200K Canadian dollars per annum. I think it's good to find a sponsor if you can, or it's good actually to connect with IBM in your area. And because also there are like Qiskit Fest, some events organized people to encode during a Qiskit Fest event. They give you access to the quantum computer. So yeah, indeed, depending on the hardware that you have, running with more than 10 qubits. I said 20. They said that 30 is the maximum, but even for us with 10 qubits, yeah, it's very, very slow. So yeah, I mean, you can try. Another company is Xanadu, right? It's not such a big company, and actually they are more open to allow you to access their quantum computer. So you can actually, in my last slide also I have Xanadu, you can connect with them and see whether or not they provide such incentive. All these companies will give you some incentive at the very beginning, but because they are very interested in, in you finding new algorithms, running. I mean, they come back and say, okay, what about the speed? Are you happy about that, right? But most probably in some years, it will be even more expensive. For example, D-Wave that I mentioned for optimization, it started also in Canada on the West Coast, but now it moved the headquarters in California. It's still California and Canada West Coast. So actually their license per 1 year is $50,000 US. I don't know for how many licenses. They work actually with Amazon. They already work with big players. So they don't really need, in a way, users as us, So I would suggest that now, while these companies are interested to see really quantum advantage in so many different areas, including ours, now is the time to connect with their representatives and see what are the conditions. Long answer, but anyhow, I think it gives
Thank
you a
you.
better picture.
Okay, let's take two questions from online audience. So, okay, so one question is, which areas in wireless communication do you think will be benefited from quantum computing?
Yeah, okay, well, I mentioned that basically you can have quantum communications itself, but I didn't talk about that. And you can have, and quantum communications is really based on the channels that use photons. I mean, can be used between satellites. Again, quantum key distribution can be used, well, optical, wireless. There are already experiments, right? But quantum computing, right? It's about computing. I mean, where are you doing computing in wireless communications? Everywhere. So where exactly you'd like to see that benefit? Wherever again you have large data sizes, high dimensional features, all that, and you need your latency is really, or the computing speed, it's sensitive, right? You need to do it fast. Then for those applications, quantum computing, can be applied. I mean, there are so many. Yeah. So again, we need to make the distinction. Yeah.
Yeah. So another question is, does hybrid quantum classical neural network approach not look like the hidden Markov model like approach?
I don't think so. No, I don't think so. Yeah. Well, there are probabilities there, but not really. Yeah. No, I would say no. Yeah. Okay.
Yeah. So we can stop here.
Yeah.
So other audience, if you have any questions, so you can email. Okay.
Yeah, I'm happy to answer any questions.
So
That
we
I
have
can.
a small gift also for.